For um for today's discussion, uh, this is a the next topic for kinematics of a particle. We talk about curvilinear motion of particles, and after the rectilinear kinematics manggod, rectilinear motion rather, um, the next topic for kinematics is about the um, motion of a particle in a curved path. So that is what we call curvilinear motion. So I start on the general curvilinear motion, that is more on the introduction, and then the um, afterwards is the um, rectangular components for curvilinear motion. Then after the rectangular components is introduction, more on introduction on the projectile motion. So for the curvilinear motion is um, even though we discuss about the motion of a particle in a straight line path that is in rectilinear motion, naiuban particles pod or object that will move in a curved path. So that's why it's very important that you also know how to describe a motion of a particle, not only in moving in a straight line path, that is what we discuss in rectilinear motion, but also you need to know how to describe the motion of a particle moving in a curved path. So let us discuss on the general curvilinear motion. So when we talk about curvilinear motion, this is when a particle moves along a curved path. And for curvilinear motion, since this path is often described in three dimensions, vector analysis will be used to formulate the particle's position, velocity, and acceleration. So for curvilinear motion, what we actually discuss here, like what I've said earlier, are rectangular components, projectile motion, tangent and normal, cylindrical, and lastly is the relative motion. In terms sa curvilinear motion, mas better siya i-describe in three dimensions, um, especially that we apply vector analysis. But in terms of three dimensions, ma-encounter nato na siya when we discuss on cylindrical. Mostly ang atong ma-discuss ani, especially sa example problems, are in two dimensionals or two dimensions. And for the geometric aspects for curvilinear motion, we will discuss also its the position, velocity, and acceleration of a particle that is moving along a curved path. So let us talk about its position. So for its position, we let us consider a particle located at a point on a space curve defined by the curve um, by the path function st. So we have this image here, and the position of the particle is measured from a fixed point O, which will be designated by the position vector r, which is equal to rt. And if you notice that both the magnitude and direction of this vector will change as the particle moves along the curved path. So if, as shown here in the figure, if the particle is moving along the curved path, the when we measured its position, it is measured from a fixed point, say here in our figure that is point O, and if it is moved along a curved path, its position, the magnitude, both its magnitude and direction will change. So say kung naa nga to ang kung nangato ang particle here, so I will just there. So kung nag-move ang atong particle here, so we measured its position from a fixed point. So that is from point O. So mo nang iyahang position. So let us say that is R1. So kaning magnitude and direction ni R1 is not the same sa iyahang initial position, which is measured from its position vector R. So the same thing if it moves here, ang ato ang particle, it will have a different position vector. Say that is R2. So that's why when a particle is moving along a curved path, both its magnitude and direction will change. Afterwards is we discuss its displacement. For displacement, suppose that during a small time interval delta t, the particle moves a distance delta s along the curve to a new position that is defined by r prime, which is equal to r plus delta r. And the displacement delta r, which is defined by delta r, represents the change in the particle's position and is determined by the vector subtraction, that is delta r is equal to r prime minus r. And this is a representation of the displacement. So, like what I've said kanina, if a particle is moving along a curved path, if it has a new position, when you measured its position vector, which is represented by vector r, it's both its magnitude and direction will change. And for its displacement, if you notice here, it is represented with symbol delta r. So, on siya. And if I enlarge this one, this is not actually the same with the measurement of delta S. Kaya kung mag-ingon tag delta S, that is actually the length of your curve, the arc length mismo. So I'll just enlarge that portion. So kung naadiri si ang initial position ni particle and naadiri ang iyahang final position, so mo nang iyahang the curve path. So ang nag-curve, that is the delta S. So ang nag-curve, mao nang iyang delta S, that is the arc length. Ang iyahang delta R, that is actually a straight line. So if we measure it from the initial position going to the final position, that is what we call the displacement. So it means that that is the change of its position from its initial to its final position. So that's why in this figure, medyo dili siya maklaro sa koan, dili sa gidisplay na figure, but when we enlarge that, the delta S and delta R are different. So the change in the arc length, which is the delta S, is not equal to the change in position, which is represented with delta R. So for the delta R, speaking of delta R, we will actually use that to determine the other geometric aspects, that is the velocity and acceleration. So for the velocity, during the time delta t, the average velocity of the particle is defined by the following. So the same happens sa rectilinear motion. We have actually average and instantaneous velocity. So for the average velocity, that is defined by delta r over delta t. And if you notice here, um, the letters of V and R are naka-bold face letter, because this represents a vector, both the average velocity and also the um, change in position or delta r are vectors when we analyze in the motion of a curved path, that is motion of the particle that is moving along a curved path. And speaking of the average velocity, we have instantaneous velocity. So that is determined from this equation by letting delta t approaching to zero, and consequently the direction of delta r approaches the tangent of the curve. Hence, we have this formula. So the instantaneous velocity is equal to the derivative of your position, which is the r, with respect to t. So that is dr over dt. And since dr will be tangent to the curve, the direction of your velocity is also tangent to the curve. So for that, when we describe the location of the velocity of your particle that is moving along a curved path, that is always tangent to your curve. So as shown here in this figure, kung makita ninyo, ang velocity sa imuhang particle is always tangent to the curve. And the magnitude of your velocity, which is called the speed, is obtained by realizing that the length of the straight line segment delta r approaches the arc length delta s as delta t approaches to zero. So when we actually determine the magnitude of velocity, which is the speed, we actually use the arc length, which is the delta s. So that's why the speed or the magnitude of velocity is equal to ds over dt, or the change in arc length with respect to time, or ds over dt. Thus, the speed can be obtained by differentiating the path function s with respect to time. So it is actually the same of the rectilinear motion, atong first kinematic equation nato na v is equal to ds over dt, which we use the arc length or the delta s as delta t approaches to zero. The other geometric aspect that we need to discuss is the acceleration. The same siya sa velocity, we have also um, average and instantaneous acceleration. If the particle has a velocity v at time t and a velocity v prime, which is equal to v plus delta v, that is the final velocity, or the the final velocity, or the another velocity at another position at t plus delta t, then the average acceleration of the particle during the time interval delta t is defined by the following formula. So that is delta v over delta t. So the delta v is the change in velocity. So that is the final minus the initial velocity, v prime minus v. So as shown here in this figure, 'di ba, what I mentioned kanina, ang velocity niya kahit in every position is always tangent. So, kaning v and v prime are always tangent to the curve, which are the velocities. And when we determine its acceleration, we can use this um, velocities to form a curve, and that curve, that red colored curve, is defined as, or that is what we called rather as the hodograph. And I don't know if you're familiar with hodograph, but hodograph is a plot of the velocity of a particle as a function of time. So ang hodograph manggod ay ginagamit man siya sa mga meteorologists na kung asa um, they analyze the wind velocities of storms. So using a polar coordinate system, di ba kung kumagkuhan mo sa polar coordinate system, ano bitaw circles. I will show you that later ang polar coordinate system. Ang pagkuhan sa polar coordinate system, dito i-plot ang hodograph using the wind velocities, and ang ma-form na curve is what we call the hodograph. And for the hodograph, it describes actually the locus of points for the arrowhead of the velocity vector in the same manner as the path S describes the locus of points for the arrowhead of the position vector. Diba ang path, the curved path of the particle can be described by the locus of points for the arrowhead of the position vector, while the hodograph can be described by the locus of points for the arrowhead of the velocity vector. So I will discuss later on about, or I will describe further about the hodograph. And for the acceleration, we have also what we call instantaneous acceleration. To obtain the instantaneous acceleration, we let delta t approaching to zero, and in the limit delta v will approach the tangent to the hodograph. So that would be a is equal to the derivative of v with respect to time, or that is the second derivative of your position with respect to time. So mo na d squared r over dt squared. And for the acceleration, like sa velocity, it is tangent to the hodograph. But in actual, but in reality, by definition of the derivative, acceleration acts tangent to the hodograph, and in general, it is not tangent to the path of motion. So take note, velocity is always tangent to the path, and the acceleration is always tangent to the hodograph. So mo nang imohang acceleration, kung i-locate mo siya sa curve path, that is not tangent to the curve path, but only the velocity. So if you notice here, ang acceleration is away to your curve path. That's why we have what we call centripetal and centrifugal forces. Are you familiar with the terms? Centripetal and centrifugal? Familiar mo, Ana? Familiar mo sa centripetal and centrifugal na mga term? Hello?
Dili, sir.
No? Centripetal and centrifugal? mura siya og kana I don't know basin wala lang ninyo na remember, but it is very common sa physics ang centripetal and centrifugal. Ang centripetal and centrifugal, this represents the tangent and normal, which we will discuss in the future about tangent and normal sa curvilinear motion. But nevertheless, for the hodograph, if I will describe further the hodograph, so if we consider a series of velocities that are tangent to your curve, so kung mao ni mo hang curve path sa imong particle, okay? And then we have every time na move ang imong particle, on imong particle, initial positions imong particle, unya nag-move ang imong particle here, and then nag-move na po dili imong particle, and again, nag-move na po siya dili, and so on and so forth. So, kana nag-move ang imong particle from its initial position, and in every position na siya corresponding the velocity that is always tangent. Okay, take note ang velocity is always tangent to the curve path on each position sa imong particle. So, natay velocity dire. So, I'll just change it the color. So, we will name that as V1. The same thing here sa second position niya. Okay, V2. There is a third position, V3. And for the fourth position, we had V4. And lastly, sa fifth position na siya corresponding na velocity. And using the velocities on the velocity of each position sa ibang particle, we can use that to construct the hodograph. So from that, if we consider the V1, V2 until V5, we can plot the hodograph itself, the curve, which is what we call the hodograph. So, the same lang atong gibuhat sa pag-describe sa path, sa curve path sa imong particle. It is measured from a fixed point, say that is O prime. So, dira mag-connect imong mga velocities. And take note, ang imong mga velocities ani have different magnitude and directions. So there are five velocities based on the five positions sa ato ang koan. So by using the velocities nimo, we can actually form the curve. And ang curve na ma-form nato is what we call the hodograph. So that is connecting the arrowhead So i-connect lang nato ang arrowhead ana. Connect lang na ako ang arrowhead. Okay. So this is what we called a hodograph. Mao na actually ato basis to describe the acceleration sa imong particle. So ang acceleration nato ani is tangent sa imong hodograph. But in reality, in reality or in general, ang velocity is tangent sa imong actual curve. Mama ni ang imong actual curve, this one. This is your actual curve path. Ang imong velocity kay tangent, pero in the actual curve path, ang imong acceleration is not tangent. Okay, so mao na ang difference between the velocity and the acceleration. So that is on the introduction. That is the introduction on the about the general curvilinear motion.